Okay, we're going to go over the answers here to the 7.2 quick check. So I've rewritten over here the equation. Okay, we have 3 oxygens turning into 2 ozone molecules. Now what we're asking for is find the average rate of disappearance, find the average rate of disappearance of the oxygen, so this chemical here, in the first 0.05 seconds. Well, if we're looking for a rate, one of the equations we need to remember is that rate, is defined as the change in the concentration of O2 divided by the change in time. So the change in the concentration over the change in time. Well, all we have to do is look at those two numbers to get the change in concentration, and look at those two numbers to get the change in time. So the change here is going to be 0.100 minus 0.078. So we can kind of do that in their head, and we're going to get 0.022, okay, moles per liter. And we're divided, here is the difference in time is 0.05 seconds. So the rate is going to come out to be 0.44 moles per liter per second. So that's our first answer. Now, the idea is if we wanted to, we know that we're talking about the O2, so if we wanted to figure, well, what's the ozone doing, okay, we can take that 0.044, 0.44, let me clean that up. Moles per liter per second. We're going to divide by 3 and multiply by 2, and that'll give us the answer here. So if I divide by 3, it's going to be 0.1456, like that, times 2. So that's going to come out to be about 0.29 moles per liter per second. So what the rate of the appearance of the oxygen, okay, so 0.44 moles per liter per second, divide by 3 times 2, and we get 0.29 moles per liter per second. So that's our second answer. Now, what's the rate of the reaction? Well, the rate of the reaction, all I have to do is take this number and divide by 3, or take this number and divide by 2, and I'm going to get the rate of the reaction either way. So that's going to come out to be, the rate of the reaction will be 0.15, 0.146, something like that. Now that's moles per liter per second again. Now the reason this works is just to divide by this number, or to divide by this, that the rate of the reaction is going to be the rate every time one of these reactions occurs. 3 O2s turn into 2 O3s. Well, so this is the rate, 0.44, for 3. For the rate of the reaction, is going to be 1 time through this reaction, so it's going to go 1/3 as fast, so 0.44 divided by 3. Or this is going to be formed, and I could say that's being, every 2 of those are formed every time one reaction occurs, so the 0.29 divided by 2. So either of those rates divided by their coefficients will give the rate of the overall reaction. One other thing that should be noted, and that is if it didn't say, rate of disappearance and rate of appearance, if we said just what's the rate, then this number would be a negative 0.44 moles per liter per second, and this would be a positive, 0.29 moles per liter per second, because of the fact that the reactant chemicals are going down, so that would be negative, and the product going up. But the fact that we use the word disappearance and appearance, we don't have to worry about the signs. We'll just use the positive numbers. The rate of the reaction, however, is always a positive number. Now, next one is for rate laws. So given this rate law, A plus B turns into products, that equation. So what's the rate law for this reaction? We can start off and say, okay, just the equation given, with that we can start off writing the rate law. So the rate is a rate equals K, and this is called the rate constant, times the concentration of chemical A, and that's to some power. I'm going to call it X, and Y No, that's not y. B, and that's to some other power. We're going to call that y. So we're going to figure out x and y, and that'll give us our rate law. Now we're going to do this by looking at our data, and here the important parts, we see that we have data right here where the b is not changing. So that's important because that means any change in the rate is due to the change in the concentration of A. So that's going to let us figure out the value of X, or the order for the chemical A. In the same way, we can see that here, okay, the A is not changing, so any difference in B, okay, is going to cause a difference in the rate. So we can use 3 and 2, or we can use 2 and 1 to figure out x and y. So let's go back and let's figure out our value here for the A first. So we'll go back, just use red. So we're saying, what's the change in the rate? Okay, so I have equation 3 and trial 3 and trial 2. Well, trial 3, okay, is larger than 2, so I'm going to say I want to look at trial 3 over trial 2. So what happens? I have 0.810 divided by 0.03, and that equals 27. So if I look at 3 compared to 2, the rate has increased by 27. Now B, its concentration has not changed at all, so any change that caused that rate must be due to the A. So how did the concentration of A change? So that was 0.3 over 0.1, and so that's going to come out to be 3. So I'm saying that 3 to the x power is equal to 27. So that little x up there must be, something 3 to some power equals 27. Well, we know that x is going to be, these orders that we do could be a 0, okay, it could be 1, could be 2, could be 3, and pretty much those are the only major possibilities we're going to have. So we know if it was 3 to the 0 power, this would be 1. If 3 to the first power, this would be 3. 3 squared, this would be 9. 3 to the third, so 3 times 3 is 9, times 3 is 27. So that's what it is. X is a 3 up here. So we're going to make that a 3. Now we'll go back to the other one, and this one is actually a little bit easier. If we look at the data, that let's say that A stays constant, okay, B goes up by a power of 4 times, but the rate doesn't change. So what we're saying now is what happens, okay, where the rate is equal to, if we divide the two rates, so if I do 2 over 1, and look at that data, the rate is the same both kinds, so the rate is equal to 1, and what has happened to the 0.4 over 0.1, that's 4, so 4 to the y power equals 1. Well, if I look at my possibilities here, the only possibility to make it come out to 1 is 0. So 4 y must be 0. So this is to the 0 power right here. Now let's go back and clean this all up. So we're going to say is rate equals k to the times a to the third power times b to the 0. So we'd say it's third order with respect to a and 0 order with respect to b. And so we would just rewrite that and say rate equals k times the concentration of A to the third power. So this part along with this part, that would be my rate law. And then we don't have to put the B in. So what are the value in units for the constant? Okay, what we have to do is take our rate law and we're going to solve for K. So I'm going to say K is equal to the rate divided by the concentration of A cubed. Now I'm going to go back and just take any of my trials, and I'm going to go ahead and take trial 1, like simple numbers. So my rate is 0.0300. The units for that are moles per liter per second. And that's going to be divided by the concentration, which is 0.1 molar. But that is all cubed. So on the bottom here, I'm going to have molarity cubed. So 0.1 cubed. So if I do this, I say, okay, well, dividing by 0.1 is the same thing as multiplying by 10. So I'm going to multiply by 10, multiply by 10, multiply by 10. So my answer is 30. And what happens with my units? Okay, my seconds are going to be on the bottom. And that's going to always happen. We're always going to get the time unit on the bottom. And here I have molarity to the first power, molarity to the third power. So I'm going to end up with molarity to the second power on the bottom. So my units then are 1 over molarity squared seconds. So here's my answer, 30, 1 over molarity squared seconds. Now you may also see this sometimes as 30 molarity to the -2 seconds to the -1. But that's how we do this kind of problem.